Okay, welcome back once again, guys. Look at 6.8. Some of this material we've already covered. If you recall from 7.5, when we were analyzing the graphs of those quadratic functions, we had to be able to determine where those functions were increasing or decreasing, and/or decreasing. And then furthermore, if they had a minimum or a maximum, okay? And that's what we're going to look at today in a little bit more detail, I guess. And then probably in part 2, we'll talk about these piecewise functions. So these are really interesting. All right, so this is, I just recopied this from the material from 7.5, okay? We know, again, let me just restate, if you're going to read a graph from left to right, and if the function is going uphill, it is increasing. If it's going downhill, it's decreasing. If it's going straight across or horizontal, it is constant, okay? And remember, these intervals are given with respect to the x-axis, and so here's those 3 examples we saw back at the beginning of 7.5. See, this function is increasing from negative infinity all the way to -1, because that's where the maximum is. And then from negative 1 to positive infinity, the function is decreasing. Similarly for this absolute value function, and then this is just a constant function right here. Okay, so let's take a look at an example. Now, I do want to say that these examples that we're looking at, guys, are just kind of made up. These are actually piecewise functions, because if you look at them, they look like they're made up of a bunch of pieces, don't they? Pieces of different functions that have all been kind of combined. All right, so we want to list the intervals over which the function is increasing, decreasing, and or constant. All right, well, this is arbitrary, but I always kind of like to start with increasing. Okay. So where is the function going uphill? Well, in 2 places, this piece right here, and then this piece over here. Okay. So this piece, it starts down here at this point, but that x-coordinate is -3. And it stops increasing at this point, whose x-coordinate is -1. So we say that from -3 to -1, the function is increasing. I'm going to go ahead and use the union operator. Remember, in the homework, sometimes they'll have you separate these with just a comma. But this function is increasing again over this segment, and it starts at this point, whose x-coordinate is 3, and stops at this point, whose x-coordinate is 5. So from 3 to 5, it is also increasing. So these are the 2 intervals, or these are the 2 sets of values for x, such that if you plug in larger and larger values of x, you're going to get larger and larger values of y. Now, where is the function decreasing? Well, it's decreasing this little segment right here. So this point starts at 1 on the x-axis, and it stops at 3. Okay? So it's decreasing from 1 to 3. And then there's one interval over which it's constant. It's constant from -5 all the way over here to -3. So from -5 to -3, the function is constant. Usually I'll ask my in-person classes, why do you guys think there is an open dot here and a closed dot down here? And the answer is because if this were a closed dot and this were a closed dot, that means it wouldn't pass the vertical line test, and it wouldn't be a function. That means that there would be one x value, namely -3, for which there are 2 different y values. Okay, so that's why one of these has to be open. This value right here is not included, but this one is. All right, let's take a look at another one. We saw one similar to this previously. This one says determine the intervals over which, again, the function is increasing, decreasing, and or constant. Okay. Well, where is it increasing? Well, over two intervals, really. The left, and look at this. It looks like it's made of a parabola, two constant functions, and then like this linear function here. Okay. So it's increasing. Since this arrow goes down, we assume that it was always increasing all the way up to this maximum, which is at -8. So we're going to say it's increasing from -infinity all the way to -8. And then it's increasing again over this segment, so with respect to the x-axis, from -3 to -2, this little interval right here. -3 to -2. And then where is it decreasing? Well, this area. So from -8 to -6, it is going downhill. Think about these as roller coasters, guys. It's decreasing from -8 to -6. Okay. And then finally, there's two intervals for which this function is constant. This interval here, from -6 all the way to -3. And then again, this interval up here, which starts at -2 and goes on forever. So we're going to say from -2 to positive infinity. All right, so now we'll get a little more practice talking about maxima and minima. Okay, these are the plural terms. And so this is the same graphic I showed you earlier. Okay, if it's a peak, it is a relative maximum. If it's a valley or a trough, it is a relative minimum. Now remember the behavior of the function at those two places. At a minimum, the function's going downhill, and then it turns around and starts going up. At a maximum, the function is going uphill or increasing, then turns around and starts decreasing. That's what actually creates the maximum or minimum, relative maximum or minimum. Okay. And then remember, again, we like to say where that maximum or minimum point occurs, and that refers to the x-coordinate of that point. But the maximum or minimum itself is the function value, which is the y-coordinate. So think about a roller coaster. You could say, what's the maximum height of that roller coaster? Well, it's going to be at a maximum, right? Or what's the minimum height? Well, that's going to be in a valley. Alright, so let's look at example 3 here. So it says use the graph and determine any relative maximum or minimum and where the function is increasing, decreasing, and or constant. Okay. Well, this function is quadratic, isn't it? And it clearly has a minimum that corresponds to this point right here. So we're going to say minimum of 2, because that's the function value, and then we'll say when x is equal to 1. Okay? So again, this just means that the smallest output that you'll get out of this function is when you plug 1 in for x. If you plug any other value in for x, you're going to get values that are greater than 2, because 2 is the minimum of that function. And then as far as increasing and decreasing, any quadratic function does both, right? It's increasing, it starts right here at the minimum, and it has an x of 1. So it starts at 1 and goes to infinity. And then as far as decreasing, Well, on the left-hand side, it was always decreasing until we get to the minimum here. So for decreasing, we'll say negative infinity up to 1. Okay. All right. Okay, I think we'll look at example. I may do this in 2 videos just because we'll do example 4 and then we'll have a separate video for piecewise functions. Alright, so same thing here. Use the graph, determine any relative maxima or minima, and then where is the function increasing, decreasing, and or constant? Well, look at this one, guys. Look at the nature of this function. The highest power of x is 3. This is a cubic function. This is just a transformation of that basic x cubed function. Okay. Now it's a transformation such that it's been shifted some. It actually goes up, then comes back down, then goes up again. Okay. All right. Well, looking at this, you can see that right here we've got a relative maximum, and that right here we have a relative minimum. Okay, so I'll label each of these max and min. So we'll go ahead and do the maximum first. So it has a maximum of, fortunately for us, these coordinates are given to us. Okay, the coordinates of this point, the y-coordinate is 2.370 when x is equal to, and then we've got this negative 0.667. And then we've got a minimum of, that corresponds to this point, a minimum of 0 when x is equal to 2. Okay? Alright, and then what about those intervals? Increasing, decreasing, and constancy. Well, it's increasing in over 2 intervals, this piece right here, and then this rightmost piece. So this piece was always increasing, and it stops right here at this point. Well, what's the x value of that point? What's given to us, right? Okay, so it's increasing from negative infinity all the way to negative 0.667. Oh, and it's increasing again from this minimum onward. Okay, so the x-coordinate of this point is 2. So from 2 to positive infinity. And then it's decreasing in between that relative maximum and minimum. Okay. So it's decreasing from, the x-coordinate of this point is negative 0.667 to the x-coordinate of this point, which is 2. Okay, so in between, our function is decreasing. Okay, guys, so, if you had a function that kind of modeled, let's say, we talked about our lemonade business before, but let's say you have a business and you come up with a function that models the profit or the number of sales, let's say for last year, because you have all that data. And we don't really cover how to develop a function or construct the function from data. That's kind of done in another course. But basically, guys, it's kind of the opposite of when you graph a function, you're kind of plotting points and trying to figure out its shape. If you're trying to come up with a function that models the data that you have, you basically plot all those points or plot all that data, and then you use some math to figure out what function would have a shape that kind of goes through all those points. Okay, it's called like regression. You do some kind of regression on that data. And so let's say you had a function that modeled or represented the sales of the previous business year. And you could look at that function. You could say, well, where over what values of X or what time of the year are my sales increasing? What time of the year are my sales decreasing or increasing again? So, you could see some kind of oscillating behavior there. And that might inform you about future years, when you need to have more inventory or carry less inventory perhaps. So anyway, all right, well in part 2 we're going to discuss these piecewise functions.